This next problem, number 60 from chapter 21, I found to be a little puzzling the first time I looked at it. And this problem is it's a variation on an example that was presented earlier in the chapter, example 21.2, page 579. Of course, this is for the 4th edition of our book. And what puzzled me about the problem is that it was the fact that I was under the impression that if you take an ideal gas around a closed cycle in the PV diagram, that cycle constitutes either a heat engine with useful output work or a refrigerator / heat pump in which heat is drawn from a cold reservoir and dumped into a hot reservoir. So it hadn't occurred to me that there were at least one other possibility, and that's what this problem is about. Now this is the, you're looking at the graph that was presented in the example. Notice it's a clockwise path, which I will indicate with my laser pointer. This is a clockwise path in the PV diagram, so we know that that constitutes positive work done by the system. WS is positive. The work done on the system would be negative. So usually we would call that work out, useful output work done by the system. And they've given us at least one of the isotherms here. And if you think about it, we're at position, or when you're at position 4, you know the pressure, the volume, and the temperature, PVT. You can solve for N, and then we can use our various formula for the special ideal gas processes to solve for all the other quantities, because these are, we've got 2 isobars and 2 isocores. We know how to handle those. So in this problem, the only difference is that we're going around the cycle backwards. Yeah, just a reminder here, the work done by the system here is positive. This is the graph presented in the solution. So there's already some information here, kind of a giveaway, spoiler alert, but let's briefly see if we can explain some of what they've given here. The temperature here was not stated in the problem. This is from the solution. But let's look at the heats here. First of all, let's check the directions of the arrows. And notice how they've kept the same numbering scheme. If you go around clockwise, they're still numbering those 4 states, 1, 2, 3, 4. But because we're going around counterclockwise now and starting here, the second state in the sequence would actually be state 4. So in my spreadsheet, because I will do a spreadsheet, I'll stick to this numbering scheme, but I'll just present them in the proper order, 1, 4, 3, 2. Okay, so this is an isochoric process. That means the box that the particles are confined to does not change volume, and yet the pressure drops. How could you drop the pressure if the size of the box stays the same? The particles would have to go slower, and that means a lower temperature. And since the temperature alone determines the energy of the gas, that means heat's got to be flowing out. And that's how they determine the direction of the arrow. The only way to be dropping down to a lower isotherm without doing work is if heat is flowing out. Remember, if you allow gas to expand adiabatically, it will also experience a decrease in temperature, because by doing work on its surroundings, its internal energy is dropping, and that would indicate a lower temperature. Here, though, there is no work being done. It's isochoric, so it's got to be losing energy because of an outflow of heat. Let's quickly go through the other 3 here. Here, the gas is occupying triple the volume. See how we go from 1 cubic meter to 3 cubic meters. Now, if you had an isothermal expansion of volume, so the particles are still moving at the same speed, but they're in a larger box, the pressure would go down because they're not colliding as often with the walls of the container. And yet here we're told that the pressure remains constant. So the only way to maintain that constant pressure, despite the particles occupying a larger volume, would be if the particles are moving faster. And so there's got to be, hang on a second. Why are they showing the heat flowing out? Am I missing something here? Oh, I see my mistake. Look at the direction of the arrow. I was going from 1 to 2. I should be going from 2 to 1. So that makes sense, since we're squeezing the particles into 1/3 the volume compared to here, and yet the pressure is still the same. That means we had to cool them off. So heat had to flow out. Lastly, I'm not going to repeat that mistake. Let me go down to 4 here. This is, here's the logic that I applied, or I tried to apply just a moment ago. If you're allowing the volume to expand, without a pressure decrease, you would need those particles to be moving faster, and that means heat would have to be flowing in here. Yeah, see how it's an isochoric process? So that means no work is being done on the gas. We're not squeezing the gas and doing work on it, and yet its temperature has clearly shot up. We're going from one isotherm to another. How can you raise the energy of a gas without squeezing it and doing work on it? You would have to transfer heat into it. So the arrows make sense. The one thing that we need to figure out then is, how did they determine that this is QC rather than QH? Because, and I'm going to show you the graphics in a minute to remind you of this fact, but sometimes energy is taken up from the hot reservoir, but sometimes it's also taken up from the cold reservoir. So you can't just go by whether it's heat in or out to determine whether you're talking about heat drawn up from or deposited to the cold reservoir, or heat drawn up from or deposited to the hot reservoir. The direction of the arrow alone does not tell you that. And I know I'm throwing a lot at you with this single graphic here, so we'll move on in just a moment. But remember, there's going to be an isotherm through this bottom left corner. There's another isotherm through the top right corner. And for this problem, I think we're going to find that there's a single isotherm cutting through both of these points. So you have to think about the second law of thermodynamics and the direction of heat flow. If heat is flowing out as we move from point 1 to point 4, if heat is flowing out, then it must be flowing into a reservoir with the temperature that's colder than the temperature of the working substance. And remember, this PV diagram tells us about the working substance. These temperatures here, these are not the temperatures of the reservoirs. These are the temperatures of the ideal gas as we take it around the PV cycle. So we're going to show, as we do the problem, that the temperature here and here is 900 kelvins. So the ideal gas in going from 1 to 4 has dropped from 900 kelvins down to 300 kelvins, and yet the entire time it is shedding heat. And that means that the reservoir to which it's shedding heat must be at a temperature less than 300 kelvins, because heat never flows from cold to hot. It always goes from hot to cold. We know that from the second law of thermodynamics. And if you're thinking, wait a minute, sometimes it does go from cold to hot because that's what a refrigerator does. Well, not exactly. The net effect of a refrigerator is to withdraw heat from cold to hot, but it happens over the whole cycle. It doesn't happen directly. So it's safe to say that you're never going to have two quantities of liquid or gas next to each other and have heat flow from cold to hot. That doesn't happen. You can get heat to go from cold to hot as your net result, but never along any individual process. Okay, so again, because we take the gas from 900 kelvins down to 300 kelvins and it's losing heat all the while, the reservoir it's in contact with would have to be at a temperature less than 300. So just keep that in mind. And then we go over here. As the gas goes from 3 to 4, it's absorbing heat, but the gas gets up to a temperature of 2700. Now, if it's absorbing heat from a reservoir, that would mean that the reservoir would have to be at an even higher temperature than the gas's temperature. And that, if you look at the upper right here, that tells us that whatever this reservoir is, whatever the temperature is, it's got to be greater than 2700 kelvins. Otherwise, heat would not be flowing from that reservoir into the gas by the time we get to this point. So we've just established there are two reservoirs here. When this gas is shedding heat, it's shedding heat to a reservoir at a temperature less than 300 kelvins. When it's taking up heat, it's doing that from a reservoir that's hotter than 2700. And there's our answer. Obviously, the one that's above 2700 is the hot reservoir, and the reservoir that's at a temperature lower than 300 is the cold reservoir. Moving on. And again, since this is a counterclockwise cycle, we know that there's work being done on the gas, and that's why they've chosen to call it work input. If work input is a positive quantity, then the work done by the system is negative. Okay, so here's the schematic to remind you of how the essence of how a heat engine works. The working substance, whether it's steam, water, freon, which they don't use anymore, some other refrigerant, or merely an ideal gas, which is the case that we're concerned with, the the working substance takes up a quantity of heat, QH, from a hot reservoir. Some of that energy in the form of heat is being used to do useful output work. That's the whole point of the heat engine. But you cannot escape the fact that some of the QH gets wasted. So here's a point I haven't made yet. You see how the thickness of this bar plus the thickness of this bar equals the thickness of this bar? That is merely the first law of thermodynamics, the conservation of energy. That's it right there. The thicknesses have to, that equation has to balance in order that energy be conserved. Whatever energy is drawn from the hot reservoir has to go somewhere. So that the various contributions have to sum up to the original thickness, as I'm calling it. And you've seen or you've read that there's no way to get rid of this QC, to eliminate that from the diagram. It has to be there because the second law of thermodynamics tells us it's impossible to convert all of this heat into useful output work. And there are various ways of proving that. And that the clever one that's presented in your book is that if you could do that, there's a way of using that heat engine to run a refrigerator that would cause heat to go from cold to hot with no other effect. So maybe I'll get to that in a later video, but it's worth pondering that proof in your book. Okay, the refrigerator is like a heat engine in reverse. You're taking your ideal gas around the PV diagram in the opposite sense. So the effect of the input work, and in the case of your kitchen refrigerator, that's electrical energy from the power company. It induces a flow of heat from the cold reservoir to the hot reservoir. And you must have the input work. So it's impossible to have the thickness of the QH bar here be just equal to the thickness of QC. If you could somehow get rid of this, then you would have a process by which the only effect is that heat flows from cold to hot. We know that that doesn't happen. That's a violation of the second law of thermodynamics. So you must have input work. And notice how this diagram is really just this diagram with the arrows reversed. All three arrows have been reversed, right? Yeah, that checks out. So I thought that was it, that those are your two possibilities. But we're going to see that the, I hesitate to call it the engine, but the cycle that we look at in this problem is really neither of these pictures. Okay, here's some equations worth knowing. These are just mathematical statements of what you can see from the picture. The heat absorbed gets broken up into two outputs. There's the output work and then the heat that's dumped into the cold reservoir. Over here, the equation's slightly different. Instead of calling it work out, we call it work in. It's understood that work in is a positive quantity and also that work out is a positive quantity. So here, the overall heat that gets dumped into your kitchen, the air of your kitchen, would be the heat taken out of the interior of the fridge plus the electrical energy withdrawn from the electrical plug socket. You know what I'm trying to say. The energy that you drew from the power company. Again, these are just statements of conservation of energy. That's all they are. That's the first law of thermodynamics. And here's a point worth noting. This is going to help us figure out what's going on with this particular cycle in this problem. When you look here, a requirement for a heat engine is that QC, and remember QC is a positive number always. It's the absolute value of all the negative Qs of your, it's the sum of the absolute values of all the negative Qs in your various processes. That has to be less than QH if there's any useful output work, okay? QC is less than QH for a heat engine because some of QH was used for output work. That's the whole point of the engine. And you know what this says, as required by second law? I don't think I need that statement. That is erroneous. Let me get rid of that. This is the statement I intended to make. The output work must be less than the heat drawn up from the high temperature reservoir. Otherwise, you would have a perfectly efficient heat engine, and we know that that's prohibited by the second law of thermodynamics. There is an upper limit on the efficiency. That's the Carnot efficiency. Okay. Oh, you know, I see what I did now. My apologies. This equation was meant for this diagram. I had it right the first time. Let me fix this one more time. This inequality refers to the refrigerator. Why is it that QC must be less than QH? Well, remember, work in plus QC has to equal QH. That's conservation of energy. So if QC were equal in thickness to QH, that would imply that there was no W in. In other words, heat would be flowing spontaneously from a cold reservoir to a hot reservoir without the input of work. And we know that that's a violation of the second law. All right, so I've taken the liberty of adding a couple isotherms here. I already mentioned this. We're going to show where this number comes from, and I really should have done a third isotherm that I believe passes through both of these. That's the 900 Kelvin isotherm. Oh, I'm getting ahead of myself. That was a diagram indicating what this PV cycle is actually doing. So let's go now to the spreadsheet, and I'll move through this rather quickly since we've done this a couple times now. It's probably getting a little tedious, but this heat engine or this PV cycle is different, so the practice is worthwhile. And actually, before I switch over to Excel, take a long look at the diagram here. And you have to ignore some of the information because we're not supposed to know it. This 2700 was not given, and the directions of the arrows were not given. All we really knew or know from the statement of the problem is where the vertices are located on the PV diagram and the fact that this bottom left corner, state 4, is on the 300 Kelvin isotherm. So let's try to memorize the various volumes and pressures. So it's a square, that makes it easy, or a rectangle. And the volumes are 1 and 3 cubic meters. That's easy, 1 and 3. And same with the pressures, 1 and 3. So I think we can reconstruct all of that from memory, and I won't have to go back and forth between the spreadsheet and here. So 300 kelvins, and then 1 and 3 along the two axes. This is a now familiar process. I'll start with the value of R in SI units. And we know that the constant volume heat capacity for a diatomic gas, so it was specified in the statement of the example on page 579, I think it was, that we're talking about a diatomic gas that's 5 degrees of freedom for typical temperatures. So it's going to be 5 times R over 2, because there's R over 2 per degree of freedom. Constant pressure molar heat capacity is CV plus R. And then let's fill in the data that we know. So remember, we're going counterclockwise now. Was it counterclockwise? Yes, counterclockwise around the PV diagram, starting in the upper left, starting at state 1. So these numbers are out of order because they actually do follow the order in which we encounter those states in the cycle. This is top left, bottom right, top right. Okay, the pressure, that was the 3 atmospheres. Let me start with the one on the bottom. This is bottom left at 1 atmosphere, which would be 1.013 times 10 to the 5th in SI units. And pressure at point 1 was 3 atmospheres, so that would be 3 times the pressure here. And then those top horizontal lines, those are isobars. So state 3, that's bottom right. That would be the same as pressure at bottom left. And then top right, that's state 2. That's going to be the same as the pressure at state 1, which is the 3 atmospheres. I believe I've done those correctly. Now, bottom left is the one that's at 300 kelvins. Bottom left was state 4. So this is the 300 kelvins. And again, I've got these 2 columns because I'm going to do a check on the temperatures. For this one, it's trivial because it's given to us. And you know what? I probably will go back to the diagram so I can use the proportional reasoning here. Yes, I'll do that to figure out what the temperature at state 1 is. Even though the arrow points down, let's imagine going from 4 to state 1 in order to figure out what that temperature would be. Well, if the volume's not changing, but you've tripled the pressure, the only way to do that would be to have the particles move around faster. So use proportional reasoning with the ideal gas law. Triple the pressure would have to mean triple the temperature. So we've gone from 300 kelvins to 900 kelvins. And then while we're here, instead of switching back and forth, what about if we went from 1 to 2? Again, the actual gas is being taken from 2 to 1, but you you can flip it around in order to figure out what the temperatures are. Normally, if you allow the volume of a gas to increase, the pressure would drop because you've got fewer collisions with the walls, and yet the pressure remains the same. So the only way to expand that box and maintain the pressure would be to increase the temperature. And the volume's going from 1 to 3 cubic meters. We've tripled the volume, so we must be tripling the temperature. And that's how we went from 900 to 2700. Now for the last one, just undo the proportional reasoning. If you went from 2 down to 3 without changing the volume, so you're not squeezing the particles into a smaller box, so how is it that the pressure's dropping? Well, it means the gas particles are having to slow down. That means less temperature. So if we've cut the pressure from 3 to 1 atmosphere, then we must have cut the temperature by a factor of 3 as well. So that's 2700 back down to 1/3 of 2700 or 900. So yes, indeed, these 2 points are on the same isotherm. Having gone through all of that, I'll see if I can fill this all out at once. Well, the volumes are easy because those are given, right? We were dealing with 1 or 3 cubic meters. So let's go around counterclockwise. State 1 was at the 1 cubic meter volume. State 4 directly down, also at 1. I don't really need the equal signs here, but oops. Then we go over to state 3, that's bottom right. That's got 3 cubic meters volume. And isochore straight up to state 2, also 3. Okay, and now the proportional reasoning that I just went through. Remember I was imagining going from the bottom left to the top left. In order to triple the pressure, I would have to triple the temperature. So this temperature should equal the temperature at the bottom times a factor of 3. And then to go from state 4 to state 3, that's, so here's bottom left, here's bottom right. You know what, why don't I go from top left to top right? That's how I walked you through it in the diagram. Remember, if we're at 900 kelvins, but we triple the volume while maintaining the pressure, we would also have to triple the temperature. So this is going to be 3 times the temperature at top left. There's our 2700. And now going from here to here, see that from state 2, which is top right, to state 3, which is bottom right, that's when we dropped the pressure by a factor of 3 without changing the volume. That would require cutting the temperature down by a factor of 3. So we went from 2700 back down to 1/3 of that. Okay, now as a check, we could use the ideal gas law to confirm all of these. Because in PV equals nRT, T would be PV over nR. So to confirm the 900 kelvins, let's take the pressure at state 1 times the volume at state 1 divided by R and divided by N. Oh, we don't have N yet. I'm going around in circles. I should use state 1 to find N. Yes, okay, I'll leave this temperature blank. Or I guess to be really correct here, the state for which we had all the information originally was bottom left. That's this state. Okay, I'll use this state to get the number of moles first. Okay, PV equals nRT says that N equals PV over T. So this equals the pressure at state 4 times the volume at state 4 divided by cell C3, that's R, divided by the temperature that was given, 300 kelvins. Okay, that's how we determine the number of moles. See how many moles this is? One of the other problems we did was way less than 1 mole. Now we're talking about 40 moles. This is a lot more gas. We should expect a lot more output work. We're talking maybe thousands of joules, tens of thousands of joules. Okay, now we can go ahead and use the ideal gas law to check the temperatures since we now know the number of moles. This temperature should be PV over nR, pressure at state 1 times volume at state 1, divided by number of moles, divided by R. Do we get 900? Yes. Okay, this is the one we already knew. That's trivial. And the temperature at state 3 should be the pressure at state 3 times the volume at state 3 divided by the number of moles divided by R. you really should, maybe you're doing this with a spreadsheet as well, which is great, but because you can't submit a spreadsheet with your exam, make sure you know how to do this on paper as well. Especially this part down here, make a little table with a ruler, columns and rows, and get some practice filling that out by hand. Lastly, the temperature at state 2 should be pressure at state 2 times volume at state 2 divided by N divided by R. This is becoming rote. Feels like a kid could do this. All right, remember, as we go counterclockwise around this process, starting at the upper left, we first go from state 1 to 4, then from 4 to 3, then 3 to 2, then 2 to 1. So I'm keeping the same numbers that were in the original diagram on page 579. Okay, and now we'll use a combination of definitions of heat capacity, the calculation of energy using CV, and the first law of thermodynamics, or the definition of work, to fill in the rest of the chart. Because ultimately we're interested in what's QH, what's QC, can we even define an efficiency for this? What are we even doing here? Okay, process 1 to 4, that's starting in the upper left, dropping down to the bottom left. That's an isochore straight down. Isochore is constant volume. How much heat is required to change the temperature at constant volume? We have a definition for that. It would be the number of moles times the constant volume molar heat capacity times the change in temperature. Since we went from state 1 to 4, that would be temperature T4 minus temperature T1. Okay, and now we've confirmed what the solutions manual was telling us. As we drop down that isochore, heat is leaving. There's heat flowing out of the working substance. What about the work done? It's an isochoric process. It's 0. That's easy. Okay, and then for filling in delta E, you could do it this way. You could recognize that I'm not going to switch back. You know what? I will. Hang on a second. Once again, chapter 21, we like to write the first law like this. When you put heat into the ideal gas, it can show up in 2 ways. It can allow the gas to do work or increase the gas's internal energy. No work is being done here. So whatever heat flows in or out, that's the same as the change in energy. Back to the spreadsheet. So I could just set these equal to each other, but as a check, why don't we imagine that we went between these two temperatures using a constant volume. Hey, we did go between these temperatures at a constant volume process. So it would be totally redundant to do NCV delta T, because that's how I got Q. Okay, I'll just set it equal to that. This one was easy. 4 to 3, that's bottom left to bottom right. That's an isobaric process. Aha, for an isobaric process, the work integral is trivial. Integral of PdV is the work done by the system. If pressure is constant, as it is in an isobaric process, you just pull the P out. The integral of dV is delta V. So again, this is just equal to P delta V. That's one of your special formulas. Well, the pressure from 4 to 3, I could use either of these pressures. It's that many pascals times the change in volume. So volume final is 3, bottom right. Oops, not pressure. Final volume is 3, volume 3, happens to also be 3 cubic meters minus the volume at state 4, which was 1 cubic meter. Okay, now it makes sense that the work is positive because we're going to the right on the PV diagram. Now, how do we find Q? Do we need to use the first law here to do this? No, because since it's a constant pressure process, we can use the definition of constant pressure molar heat capacity. Remember, for a gas, which is free to expand, unlike a solid, you can really only define the heat capacity for 2 special processes, isobars and isochores. If you took some random trip across the PV diagram, there is no definite heat capacity as there might be for a solid. So this would be equal to the number of moles times the constant pressure, molar heat capacity, because this is an isobar, times final minus initial temperature. We're going from state 4 to state 3, so final temperature would be T4, pardon me, minus temperature T3. Okay, so heat is leaving. Interesting. Is that obvious from the, well, we already went through this. It's escaping me at the moment why heat is leaving, but let's do a check here. The change in energy. Well, we've gone from one isobar to another. We went from the 300 Kelvin isobar to the 900 Kelvin isobar. And that means the energy increased, and we can always use CV to find that for an ideal gas. Number of moles. Even though this was not a constant volume process, we can still use the definition of constant volume heat capacity. NCV times the change in temperature. So that would be T3 minus T4. Here's the temperatures, T3 minus T4. And I have a feeling that I did something wrong here. I must have. Let me check this formula here. NCP delta T. So that's number of moles, C4 times, okay, C1 times final minus initial temperature, which should be T3 minus T4. That would be J cell J4. Aha, I've got these backwards. I knew something was up there. I had my temperatures in the wrong order. Okay, now this makes sense. Think about the first law as I just wrote it on the notes. This is the heat flowing in to the gas during that isobaric process. Where does that heat show up? Some of it is used for output work. Some of it raises the temperature of the gas or the energy. And let's do a check, because this was calculated using the definition of work, the integral of PdV. But let's use the first law just to check. Whatever's left over for output work should be equal to the heat drawn up minus the energy used to raise the, minus the heat used to raise the energy of the gas. I'm just using the first law. And see how we get the same answer? That's reassuring. Process 3 to 2, that's from bottom right to top right. Again, isochoric process, trivial, no work is done. Also trivial to find the heat. Isochoric means we can use the constant volume heat capacity to find the heat that was required. Number of moles times constant volume molar heat capacity times final minus initial temperature. Well, the final temperature is T2. And the initial temperature was T3. So quite a bit of heat is drawn up in this last isochore. And that makes sense because we've shot up from 900 kelvins all the way to 2700 kelvins. It's a big change in temperature and a correspondingly big change in energy that's got to come from the heat. Remember, there's no work being done. So we're not increasing this gas's energy by squeezing it. We're only increasing the energy by dumping heat into it. And just like before, there's no point in me doing NCV delta T here because that's exactly what I did for Q. Let's just recognize that according to the first law, if none of the heat is used as output work, then all of the heat shows up as a change in the thermal energy of the gas. Okay, let me get rid of the stupid error message here because that's going to make me OCD. Maybe I shouldn't trivialize that diagnosis, but everybody does that, doesn't they? Or don't they? Ignore error. Okay. 2-to-1. That's top right to top left. That's an isobaric process. So once again, the work integral is trivial. We can actually do it directly. Integral of PdV becomes just P delta V. So the pressure we're talking about is the pressure at that top isobar. That is the 3 atmospheres times final minus initial. Well, the final volume is volume 1. That's 1 cubic meter. And the initial volume is the volume at state 2, which happens to be 3 cubic meters. Okay, the gas or the system is doing negative work, which means that we're doing work on the system. We're squeezing the system. That makes sense because the volume is decreasing. Because it's a constant pressure process, we can use the constant pressure molar heat capacity to find the required heat. Number of moles times Cp times final minus initial temperature. Final temperature is the T1 temperature. That's the 900 Kelvin isotherm. Minus the initial temperature, which is the temperature at state 2. That's the 2700. Okay, a lot of heat flowed out of the gas during that last isobaric process. Okay, now, here's something I haven't done yet. Instead of using NCV, I could use the first law to find the work done. Since work and Q have already been calculated, I could do it that way. Let's do it both ways. The first law says that you just look at whatever heat was dumped in or out of the system and subtract the quantity that went to useful work, and the rest is used as or to change the internal energy. So according to the first law, this should be the change in energy during that last ISO bar. It makes sense that the energy is dropping because we're dropping down to a lower isotherm. So memorize that number, negative 15, 19, etc. Now let's try it the other way as a check. Our trusty NCV delta T. Number of moles, constant volume, heat capacity, final minus initial. Final is, we're back to state one. It's the 900 Kelvins minus the initial 2,700. Same answer. Okay, so it's nice to see that check. Now for the net, I'll use this column to find the net work done. Now, I don't actually know, well, I can see from the numbers, but going into the problem, I didn't know if it was going to be output work or input work. Since it's a PV cycle in reverse, I would have assumed input work because I would be thinking, oh, this is a refrigerator, so it requires work in. Okay, so let me take the sum of everything in this column, add up the work done by the system over every process. This is the net work done by the system. So if the system overall for the whole cycle did negative work, doesn't that mean that overall positive work was done on the gas? It does. So actually this does involve input work as expected, but we're going to see it's not actually a refrigerator. So even though it's not a heat engine, that's for sure, because we don't have output work. The net work done by the gas would need to be a positive number if this were a heat engine. Just think back to the problem where we raised the box of rocks with every cycle. The net heat, okay, that would be the sum of all the Qs. Remember, this is not QH. What I'm doing right now, Qnet, that is not the same as QH or QC. It's just the sum of all the Qs, each of which has a sign. So overall, the net flow of heat for one cycle is out of the gas. And that's another Q that we're not talking about a heat engine, right? Because a heat engine would have a net Q that was positive, because the whole point of a heat engine is to take up heat overall and transform some of it into work. So this is clearly not that. Now, the change in energy, you know the answer, right? If it's a closed cycle, if you're taking your gas around right back to where it started, then the energy at the end should be the same as the energy at the beginning. It may change over each individual process, but for the net cycle, the change in energy should be zero. So we take the sum of all these, and of course we get zero. And like I said in a previous video, the first law of thermodynamics, conservation of energy, it's true along any individual process, but it's also true for the net cycle as a whole. And since there's no overall change in energy, the heat that goes in and the work done, they have to be equal, and we see that they are. So right here, we can see confirmation of the first law of thermodynamics for the cycle as a whole. Now, as far as the efficiency, does it even make sense to define an efficiency here? I don't think so. So what have I done here? I already went through this. Right, okay. Work input. Again, since the net work done by the system is negative, that means really positive work was being done on the system. That's input work. So I'm going to say the input work is the absolute value of this net work done by the system. Okay, so overall, some external agent, maybe it was electrical energy from the power company, or I don't know, you burned, oh, let's see here. I was going to say you burned coal, but no, that you burned coal to get the heat, not for the input work. So I don't know, maybe this is some handheld device that you're cranking with your hand. Wherever this input work comes from, we're looking at about 405 kilojoules, which is roughly, that's roughly like 100 food calories per cycle. So this would not be by hand because that's actually a very large quantity of energy. Yeah, to take 40 moles up to 2,700 kelvins, that's a lot of energy. That's not some kind of hand-operated device. So I don't know where this input work is coming from. They didn't specify what this engine is. Now QH, these are both always positive quantities. QH is the sum of the positive individual Qs. Because QH, or is it? Is it? Remember, we have to be careful here. I'm going to pause and go back to that first graphic. And see, I almost told a lie. I said that QH is the sum of the positive individual Qs, but we've already been through the reasoning here. The positive Qs always are when heat enters the system. So if we look at the arrows, okay, so maybe I was right. The heat that enters, those are the positive Qs for each individual process. Those are Q sub H, right. I don't want to make a general statement that heat entering is always QH. That's not necessarily true because remember, a refrigerator actually does take up heat from a cold reservoir. But in this particular problem, the heat flowing in was the heat from the hot reservoir. I already went through the argument about the second law of thermodynamics, and you look at the temperature taken on by the working substance throughout the process. If heat is flowing in, that means the working substance has to be, that means the reservoir from which it's withdrawing heat must be at a higher temperature than 2,700 kelvins. And we already found the temperature of the other reservoir. It was less than 300. So this has to be the high temperature reservoir that it's taking heat from. And that means we call it QH. QH is the heat taken up by or from or given to the hot reservoir. The arrows could go either way. It depends on the process. But if that reservoir is the one with the higher temperature, then you call that QH. So in this case, Q is in fact the sum of the positive individual Qs. Well, that would be this one and this one. Hang on. Hold down the control button. There we go. All right, what is that? 2.2 megajoules. I see 6 places after the 2. All right, so we took up 2.2 megajoules. Now, if this was a refrigerator, remember, for a refrigerator, QH is greater than QC. They can't be equal because then you'd be violating the second law. QH is the combination of the heat taken out of the cold reservoir and dumped into the hot reservoir and the power or the energy from the power company that's also dumped into the air of your kitchen, for instance. So let's see what the QC is. Remember, QC has to be a positive number, but it's the sum of the absolute values of all the heats that left during various processes. So this is the absolute value of the sum of the negative individual Qs, this one and this one. And I don't think I did that right because I've already gone through the problem and that's not the number I was expecting. So let's see here. Oh, I see. It did D9 through D12. I only want D9 and D12. There we go. Okay, so whoa, what's happening here? This is 2.6 megajoules. What? So 2.6 megajoules of energy were dumped into the cold reservoir, and only 2.2 megajoules were drawn from the hot reservoir. What is going on? Because that is not what a refrigerator does. For a refrigerator, QH would be greater than QC. So we know it's not a refrigerator. We also know it's not a heat engine because it doesn't have positive net work done. A heat engine has a net output work that's positive. So it's neither a heat engine nor a refrigerator. Let's figure out what's going on here. Just to refresh your memory one more time, this is what a heat engine does. QH is drawn from the hot reservoir. Some of it's useful output work, some of it is dumped. as exhaust heat. A refrigerator takes heat from Q, and in combination with the input work, they both get dumped into the air of your kitchen. Now, what we're looking at is neither. As far as the direction of heat flow, we are taking heat from QH. Remember, at QH we determined was the sum of the heats that are positive. That means flowing into the gas. So this is the direction of the arrow that we're looking at as far as heat transfer, but we didn't have output work. We had input work. So neither of these diagrams works. And that kind of stumped me when I first did this problem. So here's what I came up with. There's a net flow of heat from high temperature reservoir to low temperature reservoir, but there's also an input work. So what on earth is this thing? Is it useful? Why? I mean, heat already flows from hot to cold. So that happens on its own. Why is it necessary to have input work assist with that process? So maybe there's some PV cycle and some device out there for which this serves a purpose. You know, maybe there are devices that have like multiple heat engines within them, and this might be useful as a part of a whole. But off the top of my head, I can't think of one. Yeah, I bet there's an application somewhere. If you discover one, please forward it to me because I'm curious. But here we're taking energy from the power company, presumably, and just dumping it into a cold reservoir, simultaneously allowing heat from a hot reservoir to flow into the cold reservoir. Now, maybe if you think about causality, maybe this heat wouldn't flow as quickly without the input work. So maybe it's accelerating the flow of heat. I don't know, but this is not a heat engine because we don't get useful output work. We have to put work into it. And we don't get, we're not doing any kind of refrigeration here, neither. So again, a heat engine, what you have to pay for is the heat from QH. And that means digging up coal, fracking, whatever, getting your fossil fuels, burning it. That's the heat. So you're paying for the chemical energy that you're converting into heat. And what you get out is the work. For a refrigerator, you're not paying for heat. You're paying for the input work, which is very often electrical energy from the power company. And then what's kind of meta about this is, well, where does the power company, how do they produce the input work? Well, they have a heat engine at their site where they've got a very large heat engine where they're taking up QH from the coal or whatever to produce that electrical energy. So interesting. It's like you've got a giant heat engine belonging to SoCal Edison where they are turning QH into useful output work. And then you're taking that useful output work and making it input work for your refrigerator. So it's like the energy just keeps devolving down and down till it's exhausted as waste heat by the coils of your refrigerator. Does it end there, or can somebody else get useful work out of that, useful energy? Is it possible to recoup that energy? Well, I was hoping to talk about the Stirling engine. Stirling with an I, Stirling. I may find time to talk about this, but you could actually buy one of those little handheld Stirling engines, hold that near the coils of your fridge, and then have that thing run off of it. So it's like the second law of thermodynamics. It does impose limits on how far down we can continue to use that energy. Basically, you have to continue to have a temperature difference. The power company, they've got a giant turbine inside of which, or boiler, inside of which the temperature is thousands of kelvins, and they're dumping their waste heat into a river or the ocean. And then in your house, you've got the inside of the refrigerator, which is colder than the air of your kitchen. Yeah, I'm starting to confuse myself, but you get the idea. You can't have any of this transformation of heat into work or vice versa without a temperature difference.